I can think of our change of variable equations as a transformation from one set of coordinates to another, which makes it a vector valued function. Let's look at the polar coordinates idea, right? My polar coordinates has x and y going to r and theta, and the functions we use are r equals the square root of x squared plus y squared, and tangent of theta is y over x. I can think of that as taking in a vector xy and spitting out a vector r theta. So rather than like back in chapter 13, we had a function that took in a single variable and put out a vector valued function. I now have a function that takes in a vector and takes out a vector, puts out a vector. So I kind of call this a transformation. Now, if these transformation equations have continuous first partial derivatives, then we're going to call them C1 transformations. In this case, C1 means continuous in the first derivative. Now, more often than not, instead of working from x and y to r and theta, I want to go the other way. And the reason I would want to do that is because if I look at going the other way here, then my functions are continuous in the first partial. This is a C1 transformation. This isn't. And the reason that first one is not a C1 transformation is when I take the derivative of r with respect to x, I'm going to get the square root of x squared plus y squared in the bottom. And that's not going to be continuous at 0. So this is less nice than this one. Even though they're both doing the same thing, they're switching between polar coordinates and Cartesian coordinates. The one from polar to Cartesian is nicer. Okay. I want to think about this in terms of pictures. If I have any transformation from R2 to R2, then what I can think of is I can think of having two copies of the plane. I can think of the plane I start in, the UV plane. I can think of the plane I go to as the XY plane. Domain and range, right? So a particular point over here has an image over here, a set over here. Would have some image over here. My transformation is 1-to-1 if the functions are 1-to-1 between AB and T of AB. In other words, each image has a distinct point it comes from. The only way to get the same images out are to start with the same points in. Now we know that there are many different angles that go to the same point and many different radii that go to the same point, right? We've already seen that this polar coordinate transformation is not 1-to-1. But when my transformation is 1-to-1, then there's an inverse transformation. And I mean that T inverse will also be a transformation that is C1. It might exist, but it might not be a nice transformation. So I really want to work with inverse transformations that are nice, regular transformations that are as nice as I can make. 1-to-1 is a nice, easy, convenient thing to do. Questions? If all of the equations involved in this transformation are the equations of lines, let's say the equation for x in terms of u and v is a linear equation. X equals, number times u plus number times v. And the equation for y is a linear equation. Then this is a matrix transformation like we study in linear algebra. But our example, our cosine theta, our sine theta, those are not linear. So I need to worry about what happens in the linear case. I need to worry about what happens in the nonlinear case. Ready for the crazy part of this? Because the real question is, who gives a why should I do this? I want to consider this transformation. Now, this particular transformation happens to be, in my opinion, a fairly nice one. But the reason I think that is because these equations are continuous, and they have a continuous differential. If I take the partial derivatives are 2u minus 2v, 2v, and 2u. Those are nice, easy partial derivatives. They're polynomials. So t is C1. I would like to know if I am in the UV plane, I have a square S. I would like to know what the image of S is. I would like you to draw me a picture and tell me what happens to this shape when I do this transformation. This is going to look a lot like when we found absolute maximums and minimums on the little section, the rectangle, but we had to look at each edge. So I need to look at each and every edge of this square. So I'm going to start here on the bottom and work my way around the sides, which I'll call side 1, 2, 3, and 4. And I want to figure out what happens to each of these sides so that I can draw the new picture. Side 1. What do you know about every point in side 1? Except I'm not in Y, I'm V, right? So here I know V equals 0. So that means when I write out my equations for X and Y, I know V is 0, which means X is U squared minus 0 squared. That's just U squared. And Y is 2 times U times 0. That's just 0. What do I know about the U values on side 1? U goes from 0 to 1. Is I need you to draw the parametric equations. X equals U squared, Y equals 0, for 0 less than or equal to U less than or equal to 1. What shape does that make? You have a graphing calculator. Wait a minute. Y is always equal to 0 here. So I'm only going to go from 0 to 1 along that piece. This is T of S1. It's just a piece. The only thing that changes is X, and X has to be between 0 and 1. Now, we don't go smoothly across. We speed up, right? Because as X gets bigger, as U gets bigger, we're going X is U squared. So we move quicker. What do we know about S2? U is equal to 1 there. So my equations for X is 1 squared minus V squared. And Y is 2 times 1 times V. And I know V is between 0 and 1. Graph that. Here I guarantee you it's going to be easier to do this on your graphing calculator. Set yourself in parametric mode. Parametric. X equals 1 minus V squared. I'll use T because I'm on the calculator. Y equals 2T. And then I'm only looking between 0 and 1 for my T values. I'm going to look at a small section of the graph because these two pieces meet at this corner. Side 1 meets side 2. I would expect their images to meet at this corner. So let's graph this. I see part of a parabola. And it goes up to a height of 2. As a matter of fact, I can work out the equation of this parabola from here, because this could be rewritten as V equals Y over 2, and that gives me X equals 1 minus Y over 2 quantity squared. That's the equation of this parabola. Oh, okay. Go back to my original picture up there. What do I know about side 3? Side 3, v equals 1, 0 less than or equal to u less than or equal to 1. Go back to my equations. X equals u squared minus v squared. Y equals 2 times u times v. V is a 1. Gee, that looks really familiar, doesn't it? Almost looks like the mirror image of the previous one. So if I graph that, x equals t squared minus 1, y equals 2t, I get the mirror image. And again, if I rearrange, I have the equation for the parabola that is that side. What about side 4? What do you know about the points on side 4 up in that square? U is 0, and v is trapped between 0 and 1. Go back to my equations. If u is 0, I get x equals minus v squared, and y equals 0, 0 less than or equal to v less than or equal to 1, means I'm going to go from when v is 0, I'll be at 0, 0. And when v is 1, I'll be at negative 1, 0. Hey, wait a minute. That closes off my shape. So what I have in this second picture is the image of that square. Now that's weird. This thing got turned into this thing. If I asked you to do an integral, which of those two shapes would you rather use as the region on an integral? The one with the parabolas or the one that's the square? Because the square is 0 to 1, 0 to 1. That's really easy, yes? But because I have a transformation, a C1 transformation, if I get an integral on this, I can switch back. Wait a minute. We said that R was the image of S, right? Wasn't that my previous picture here? It said that T went from S to R. So if I think of this as a region R, it turns out that if I want to integrate on that region, I can use this transformation and use the integral over S instead. Now, what do I mean by adjust here? It's this word that bothers me. Well, that adjustment is the change I make to dA. In the region S, dA is a little square, right? dx dy or dy dx, right? But over here in that funky region R, I would have to bend that square, wouldn't I? How much adjustment has to happen? That adjustment is based on the transformation. Now the symbol that has that partial uv over partial xy tells me that what I want to do is I want to put the derivatives of the destination variables. I'm going to xy. My transformation goes from uv to xy. So each row is a to variable, the destination. Each column is a from variable. And I take the derivatives of the to variables with respect to the from variables. I don't like that. Oh, I've written the notation backwards. That's why that's bothering me. It's partial of xy over partial of uv. So the x and the y, those are the froms, sorry, those are the twos. That's why it's the row of x and the row of y. Rows on top, columns on bottom. Hey, wait a minute. How does this get used? It turns out that the integral over r becomes the integral over s. But I have to change everything that was in x and y to be in u and v. And then over here, I'm going to get du dv. But I need to adjust it by the absolute value of this Jacobian. Ladies and gentlemen, a couple years ago, I had a couple of students graduate after taking this class, and they bought me this flag. Isn't it pretty? I would like to point out to the very top line of this flag is exactly the theorem we just wrote down. Only they use this symbol for the Jacobian. This has been hanging on my wall for the past 5 years. Surprise! Calc 3. Now, really what made me very amused is one student bought me a flag, the other one bought me a coffee cup. They both have exactly the same design. They didn't coordinate it at all. I don't believe it, but they didn't. Our transformation, the one we were just doing, our transformation, we had T of uv was u squared minus v squared 2uv. So this is our x equation, this is our y equation. So the Jacobian of this transformation is found by taking the derivative. Partial of x with respect to u, partial of x with respect to v, partial of y with respect to u, y with respect to v. For our transformation, what is that? Take some partial derivatives. Derivative of x with respect to u. Derivative, not antiderivative. Derivative with respect to v. Derivative of y with respect to u. And the derivative of y with respect to v is 2u. So when I do the Jacobian for this transformation, I can write it and then I can do that determinant, just like we were doing in the cross products, right? So I do it in the cross product. 2u times 2u is 4u squared minus 2v times negative 2v is negative 4v squared. That makes this a plus. Which means if I want to integrate over that screwy looking region whose boundaries are parabolas, I don't have to. I can integrate from 0 to 1 and 0 to 1, but I have to put that next to the dA. At which point my brain goes, hey, wait just a fucking second. I need x with respect to r, x with respect to theta, y with respect to r, y with respect to theta. Give me 4 partial derivatives, please. The derivative with respect to r of x. The derivative with respect to theta. Derivative cosine theta. Right, so I get minus r sine theta. Down here, the derivative with respect to r is sine theta. The derivative with respect to theta, the derivative of sine theta is cosine theta. Ready for the Jacobian of this transformation? What do you get when you do that little 2 by 2 determinant? Because I get r cosine squared theta minus a negative r sine squared theta r dr d theta. Where'd the r come from? Right here. I want to figure out how the little box changes when I move from one set of variables to the other. This is exactly what that tells me. The reason we take absolute value is because if this was negative, what that would mean is that we went from a right-handed system to a left-handed system. We turned something over. I don't care about that. I just care about the change in the area. That's why it's the absolute value of my transformation. So, because I did all that work with the problem we were doing earlier, I could ask, hey, let's do the integral over r of y dA, where r is bounded by y equals 4, y squared equals 4 plus or minus 4x and the x-axis. This is exactly the region we were looking at earlier in the xy plane. Which now means I don't have to do this integral like this. Instead of doing this integral in y and x, and trying to do this as a type 2 region dx dy, right? I mean, I could do that, right? I need the x equation on the left, I need the x equation on the right. I can do that, but it's going to suck. I don't have to. What I can say is I can say this becomes the region over the square 0, 1 by 0, 1. But in order to do that, I need to rewrite everything in terms of u and v. What was the y equation of my transformation? Not the polar one, the UV one. 2UV. What was the Jacobian of my transformation? That's actually an easy integral because it's just power rule. And the bounds are all numbers. This integral is actually really straightforward. On the other hand, if I really wanted to do this one this way, it would look like the integral from 0 to 2, the integral from, solve this for x with the negative side, so that's x equals y squared over minus 4 over 4, and this one is x equals 4 minus y squared over 4. So those would be the lower and upper bounds here. Y dx dy. I'm not sure that's nicer. As a matter of fact, I'm absolutely sure that's not nice. Look at the bounds there. That's going to stink. On the other hand, this one, every bound is 0 and 1. By the way, you should do this integral, because when you do, the answer is 2. If you really want to torture yourself over Easter, do the other one. Make sure you get 2. Is it worth it? As long as I know how to transform one set of equations to the other, but I don't always know that. Here, from the textbook, page 1058, is example 3. I want you to imagine just for a second that that's what you're given to integrate. The integral of e to the x plus y over x minus y. Somebody hit me in the head with the textbook, it'll hurt less. So, I don't want to do it. Look at the region we are given. That region looks like this. And the boundaries of that region happen to be lines look like x minus y. And that x minus y is in our integral. So if we use that in our change of variables, then I can write the transformation x equals y equals. Then I get the Jacobian. And if I work these lines back to this region, this is a left and a right, a top and a bottom. This is a much nicer region to work in than this is. And my integral becomes much easier to do. This is exactly the sort of substitution that at first glance you're like, what the am I going to do? But it works. As long as I can find that Jacobian. You'll notice that Jacobian is negative, but down here there's an absolute value, so I end up with a positive 1/2 inside my integral. Holy moly. Questions? I am going to make sure that what you have to substitute is always obviously displayed within the integrand. So like we saw the x plus y and the x minus y were in there, those are what I'm going to use. Otherwise, we're... On the other hand, if I give you the transformation and say, what's the Jacobian, now do the triple, that's... Wait a minute, I said triple. We've only done doubles. Does this work for triple integrals? Yep. If I have a transformation that is C1, from 3 variables to 3 variables, I can absolutely do exactly the same thing. My Jacobian each row is a variable up here. Each column is a variable down here. And then I do exactly the same thing. I just have to do all 3 transformations in my triple integral. That shouldn't be dA over there on the left. That should be dV. But this turns a triple integral in one coordinate system to a triple integral in the other coordinate system. Hey, wait a second. Those are our spherical coordinates, aren't they? If I do this process with these 3 equations, I get rho squared sine phi. As a matter of fact, I'm not even going to do it. On page 1059, they do it in the text. 1059. Notice there's a 0 on the bottom, right? Because this equation, z, has no theta in it. So when I take the derivative with respect to theta, I get a 0, which means I'm going to expand this across the bottom row. Just like a cross product, instead of going across the top row, I go across the bottom row. Plus, minus, plus. I do all the work. I do a whole lot of trig simplifying. There's a minus sign. Yeah, but in the integral, I take the absolute value. There's where the rho squared sine phi comes from. I didn't pull it out of thin air. Oh, it works. Change all the variables from x and y and z to rho, phi, and theta. And then I throw this onto the end and I can do my triple integral. I don't care what the coordinate set is. The advantage comes up that if I can find that transformation, then I can do the integrals in the simpler coordinate system. As long as I can figure out what that transformation gives me. Now, Reese, to your point, knowing that I need a transformation is always problematic, right? But when I look at the integrals provided to me, some of those are just nasty, aren't they? But I look at, say, 26, and I see sine of 9x squared plus 4y squared. That's an ellipse. Ellipses are really hard. If I could make it a circle, u equals 3x, v equals 2y, then u squared and v squared would give me 9x squared and 4y squared. So it's hiding in the function. Here, y minus x, y plus x, I should use those. Here, x plus y. Okay, I look at this, and that's a diamond. And x plus y is two of the sides. The other sides are x minus y. I can use those. So my goal is to look at the combination of what functions, what region, are they going to go together well. Here, I'm pretty sure my boundaries are all in terms of x minus y and x plus y. Let's use those. Without that information, I could be here forever trying to find a transformation. But fortunately, in some of them, they give them to me. Here's the transformation provided. And in some of them, I can work them out. This is 99.9% of the problem, figuring out what transformation to use. So if I've given you that part, the rest of it is algebra. Questions? Only if requested, but think about this problem right here. This problem, y minus x, y plus x, and they've given me these weird corners. I'm going to have to figure out what the boundaries are. Do I need to draw it? I might be able to do it just from the equations. I think drawing helps, but I'm a very visual person. On the other hand, in this problem, they're telling me x minus y is 0, x minus y is 2, x plus y is 0, x plus y is 3. And if I make those my substitutions, then this is 0 and 2 and 0 and 3. That's a box. I don't have to actually do any drawing to know that that's what those change to. Is the sketching necessary? No. Does it help? I think so. But that's me. More questions? Good news and bad news. The good news is that that's the end of chapter 15. Bad news, if that's the end of chapter 15, we should have an exam. Good news, you can't turn in this homework until we've had a question and answer day. We're off Thursday, we're off Friday, we're off Monday. We're back Wednesday, a week from today. That's your question and answer day. Then you turn in the homework. And then we're off because I'm going to a conference. So your exam is technically 2 weeks from Monday past, 12 days from now. The review sheet is posted between the homework, those 3 sections, 15, 7, 8, and 9, and that review sheet. You've got plenty to do over break. I'm sorry. Take some of a break, but don't let this disappear. I will see you all in a week, and you can ask me all the questions you want.